In section 2.6, we're going to discuss a very foundational definition that we will need throughout calculus and other mathematics if we go on in mathematics, and that is continuity. So continuity is this thing we kind of take for granted through most of algebra. Namely, you're used to having smooth curves that are nice, they have no abrupt changes, no weird holes in them, none of that stuff. The one exception to that would be vertical asymptotes, right? And when we deal with vertical asymptotes, we make a big deal out of them in algebra and pre-calc, right? For good reason, because vertical asymptotes are special. But we do regularly run into phenomena that require us to have discontinuous functions to model them. It actually happens more often than you might think. Now, discontinuous, well, these three graphs are all examples of discontinuous functions when you look at them. So you might be able to get a sense of what a discontinuous function is just by looking at these graphs. So roughly what it means is that you'd have to pick up your pen or pencil if you were drawing it by hand. So if I was drawing this by hand, I'd go from here to here, but then I'd have to pick up my pen and move it over and then draw again, right? So that's what discontinuity means, and it's discussed right here. So down below, if you can draw your functions graph without lifting a pencil, it's called being continuous. So discontinuity means I would have to, so note discontinuity means we would have to lift the pen, to draw the graph, right? You have to pick up the pen and set it back down. Right? That is a discontinuous graph. A continuous graph, by contrast, which is defined down below, would mean we'd never, it looks like cave, sorry, that's a have to lift up the pen. So discontinuous graphs, I would have to pick it up. And there's three main types of discontinuities that we're going to discuss, and those three are illustrated by these three graphs. Now, one other little side note is that sometimes discontinuities are either removable or non-removable, and I'll kind of show you what the difference is between those as we go. So just watch out for that. All right, like I already said, continuous means that, well, this is the actual definition. It means that at a point the value exists and the limit exists and they're the same. And I personally think it's easier if we kind of write it as a checklist. So this definition right here, right, the function is continuous at a point if the value there is equal to its limit. So that is defined by this checklist down here, in particular these three items, right? So you have to have the function value, you have to have the limit value, and they have to be one and the same. All right, so if we look back up at the top real quickly, we're violating these conditions in a couple different ways with these three graphs, and that's what makes them so interesting. So if we look at part 1, this graph right here, what have we done? Well, we have a limit, right? So the limit as we approach from either side exists. So I've got a limit over here and a limit over here, and they're the same number. So great. So I have part 2, the limit exists, but I don't have part 1 because there's no function there. There's no definition for f of c because it's a big open hole right there. So for this particular one, I am violating condition number 1, but not condition number 2. It has the limit, but it doesn't have a function value. There, and I just wrote that up. So this particular graph violates condition number 1, but not condition number 2, right? So it has a limit, but it has no function value, which, by the way, also means it violates number 3, right? So it's going to violate 1 and 3 because if you violate 1, then you violate 3 automatically. 3 is the one that comes from the other 2. So if either 1 or 2 are wrong, then 3 is out, right? Because 3 says that you have to have the function, you have to have the limit, and they have to be equal, right? Well, if you don't have the function value, there's nothing for it to be equal to. So 1 and 3 are gone for us, but 2 worked. All right, looking at the second graph, this one has a function value right there, but it doesn't have a limit because I'm going to 2 separate values. This is called a jump discontinuity, actually. So let me write that up 1 second. And I just wrote it up a little bit more here. So the limit as x goes to c of f of x does not exist, even though f of c exists. So we're violating 2, which automatically means 3 as well, but we're not violating number 1. Okay, what about the third one? Okay, so I have a function value right here, and I have a limit value right there. So the limit and the function value both exist. So 1 and 2 are okay, but 3 is not because they're not equal to each other. So this is violating condition 3, but not 1 nor 2. So even though the limit exists and the function exists, they're not equal to each other. So that's number 3. Now, this, like I said, the middle one is called a jump discontinuity. So if you want to write that, this is called a jump discontinuity. It is not removable. Continuity, and it's non-removable. You can't just fill in a hole and make it go away. Whereas the other two are removable. Removability happens when your limit exists, right? So if your limit exists, then it's removable because you could just move wherever your f of c value is or fill in an f of c value. So this one over number 1, this is a removable discontinuity. And this one over here for number 3 is also removable, right? So removable will mean essentially, for our purposes, that removable means that the limit exists. If the limit as x goes to c of f of x exists, then it's removable. The discontinuity is removable. If it does not exist, then it is not removable. That's the big difference between the two. Oops, sorry, that's off screen. I apologize. So non-removable means basically f of c. Oh, the limit, sorry. I apologize. Let me fix that. There we go. So the limit as x goes to c of f of x does not exist. That's the big difference between removable and non-removable. Removable will have a limit, right? And non-removable will not. And you can see it right here. This one had a limit. If I could just plug that little dot in, I'd be great. This one over here had a limit. If I could just move that dot up here, great. Non-removable, however, I could fill in one dot until the cows come home. It's not going to fix the fact that these two sides of this graph are going two completely different directions. All right, one other point to notice right here in the definition, which I skipped over, but I'm coming back to it. So now we know, we have a sense of what continuous means, right? Continuous means you could draw the whole thing without having to pick up your pen or pencil, and that means that it satisfies these 3 values from the checklist, right? The function exists, the limit exists, and they're the same. If it is not continuous at a point, that is referred to as a point of discontinuity. So for up above, those 3 graphs are all discontinuous at C, right? So that's a point of discontinuity. A function is continuous on an open interval. Those are parentheses right there. So it's continuous on an open interval if it is continuous at each point in the interval, right, within the interval. So a function that is continuous over all real numbers is considered to be continuous everywhere. And we've seen a lot of those because if you think about all the polynomials that we saw, right, polynomials in general are continuous everywhere. So, or sine and cosine, those are continuous everywhere. Sine of x, cosine of x, right? There's no breaks, there's no holes, they're just wave functions that go on forever and ever. Okay, so now let's apply what we've just learned to a particular graph right here. Okay, so we're going to determine the points at which the following function has discontinuities. For each point of discontinuity, state whether it is removable or non-removable and which one of the conditions of continuity it violates. Okay. So let's see here. First thing we have to do is kind of look through the graph and find the points of discontinuity. And there are a few of them. And one of them is a little harder to spot just because it wasn't in the graphs that we just saw on the previous page. Now keep in mind this graph has end points. It actually ends at 0 and ends at 5. It doesn't have arrows going on to forever. And there's three spots of discontinuity. So the ones that are kind of easier to spot are the ones that we just saw on the previous page. So we have a discontinuity right here, right, with that piece. And we have a discontinuity over here to the right of that, right here. Right? So we have a discontinuity at x equals 2 and x equals 3. But there's one other spot. if you were trying to lift up your pen to kind of draw this, you'd have to lift up your pen 3 times. So if I started over here and was drawing, I'd have to lift my pen. So that means that I have one more spot of discontinuity, and it's right there at that vertical asymptote. Okay, so let's start with the vertical asymptote. The vertical asymptote is at x equals 1. All right, and then you have to think about, is it removable or not removable, and what condition does it fail? Okay, so let me try x equals 1. Okay. So it's a vertical asymptote, and vertical asymptotes are kind of interesting because they fail all 3 conditions. They don't have a function value, right, because there's an asymptote there, so there's no function value. What's more, there's no limit. These are both going to infinity. Technically, there's no little arrows here, but of course there have to be. If we don't have dots, then you assume that it's an arrow going on forever. So that's going on to forever, so there's no limit. I mean, the limit on this side is infinity, the limit on that side is infinity. That means the limit's infinity, but that doesn't exist. Infinity is not a spot that I get to. So it fails condition 2 as well. So it fails condition number 1, right? There's no f of 1, right? This is f of 1 does not exist. It fails condition 2 because the limit as x goes to 1 of f of x does not exist. And therefore, if it fails condition 1 and 2, then automatically it fails condition 3, because condition 3 is just saying that these two things have to be equal to each other, right? So these are both not equal to each other. Matter of fact, you can say, if you want to be a little bit fancier about it, you could say the limit of x approaches 1 is infinity, but infinity is just a special kind of does not exist. All right, so it's a discontinuity. It fails all 3 of those conditions. The only other piece they want to know is it removable or not removable? So we've stated which type of conditions of continuity it failed, but now we want to know if it's removable or not removable. Well, remember, removable means that the limit as x approaches c for that function exists. That's what a removable discontinuity does. But we don't have that, right? We don't have a limit. So therefore, this is non-removable. It's non-removable because it fails condition 2. I don't know if I'm spelling that word right. Non-removable. There we go. Right? This part right here leads to it, the fact that it's non-removable. There's no, I can't just put in 1 dot and refill and make the graph continuous. It's not going to work. All right, now what about x equals 1, this section right here? All right, so for x equals 1, or sorry, 2, I'm so sorry, x equals 2, right here. Well, let's think. I have a function value right here, right? So condition 1's okay because I've got a function value. But condition 2 has got a problem because these two sections of the graph are not going to the same place. So this fails condition number 2, and also therefore it automatically fails condition 3 because condition 3 is dependent upon condition 1 and 2. So this fails condition 2 right there, right? It does not have a limit, right? Because it's going 2 different places. So let's think. Fails condition 2, and that means we have a non-removable discontinuity. All right, last but not least, condition 3, or excuse me, not condition 3, x equals 3. Maybe it fails condition 3, I don't know. Oh, it fails condition 1. So this fails condition 1 because there's no function value, right? Condition 1 and condition 3 because once there's no function value, then there's no way that the two things would be equal to each other. So this fails condition 1. Now, right, it's because there's no dot, right, closed dot. But that means that it's a removable discontinuity because it didn't fail condition 2, right? There is a limit, right? We just don't have the function value there. So this is a removable discontinuity, right? Because the limit as x approaches 2 of f of x exists. Matter of fact, I can tell you what it is. It's 3, right? So we're heading, oh my goodness, it's x approaches 3. Goodness gracious. Sorry about that. So x approaches 3. right? So the x value is approaching 3, the y value is approaching 3 because they're heading to 3, 3. So it failed condition 1 because f of 3 does not exist. This one up above failed condition 2 because the limit as x approaches 2 of f of x does not exist. Right? And then this one down here is removable because there, even though the function doesn't exist, there's a big open hole there, the limit did exist. And that's a removable discontinuity.